this lecture, we'll have a look at dynamic time series models. Specifically, we'll look at the ADL models, the autoregressive dynamic lag models. The setup for this lecture, or rather the starting point of this lecture, is the static linear regression model. So let's say that I have time series data, and to make life simple, let's say that I have only one explanatory variable x together with the dependent variable y. We assume that both of them are stationary processes, and for this simple setup, the static linear regression model is formulated like this. Note in particularly that y, the dependent variable at time t, depends only on x at the same time period t. That is what makes the model static. So let's look at a concrete example. Here is some time series data going from Jan 51 to January 2001. What we have here is unemployment rate in the United States, and HWI is it's an index of help wanted ads. So the basic idea of this index is that the higher the index, the more help wanted ads you see in the newspapers. If we have a look at the data, the blue series is the unemployment rate and the orange series is the index of help wanted ads. Now it's a little bit hard to see the unemployment data due to its size being much smaller than the index. So what you can do is, if you just right click this and do format data series and then pick secondary axis, then it will use an axis here on the right for the unemployment data and the left axis for the index, making it much simpler to compare and see what's going on. So it's pretty clear from the data that these are negatively related, right? In this period, the unemployment rate is very, very low, and at the same time, the help wanted ads increases. And we see the same thing happening here. There's clearly a reverse relationship between unemployment and help wanted, which makes sense. When the unemployment is very high, like around here, then it's much easier to find people, and the help wanted ads are much fewer, and vice versa. So let's see what happens if I try to analyze this using a static model. Let's focus on just the parameter estimates. So I'm creating just a linear regression where the index is my y variable and the unemployment rate is my x variable, including the intercept but no statistics. Shift Control Enter, and we see something that we probably would not expect, and that is that the sign of B2 is positive. Remember, a positive sign must be interpreted as when the unemployment rate increases, the number of help wanted ads also increases, which is counterintuitive to what we sort of discovered from the data, and it's also counterintuitive from an economic perspective. So we'll see that the problem is simply the fact that we're analyzing this using a static model, and by moving to a dynamic model, the problem will disappear. So with this in mind, let's move on. And the first thing I want to discuss is the concept of lagged variables. So we'll begin by looking at lagged explanatory variables. So to introduce the idea of lagged explanatory variables, Let's consider a simple example for a second. Let's say that we're thinking about monthly personal expenditures as a time series. And let's say that we have a temporary and sudden increase in income in January. Now, for most people, that would probably lead to an increase in personal expenditure in January as well. But again, for most people, you may not spend all of this temporary increase in income in January, but instead decide to save some of it for the future. So when we then come to February, when the income is back to its normal level, and we have saved a little bit of the money that we had from our extra income in January, it is quite likely that expenditures in February will be higher than normal as well, even though income in February is normal. So this is a simple example of a case where the dependent variable, the expenditure at month T, depends on an explanatory variable, the income, in a previous month. So when that's the case, if you believe that yt directly is affected by the value of an explanatory variable in the previous period, and we denote that by xt minus 1. So if t refers to February, t minus 1 will refer to January. In that case, we have a dynamic linear regression model, and it can be written like this. Yt depends on the income in this period, but also the income in the previous period. And if you want to model expenditure, then it may actually be a more realistic model that your expenditure in a month doesn't just depend on the income you have that month, but also the income you had in the previous month. And this is an argument that we believe can be applied to many cases when we have time series models. This new variable that we've added to the regression, xt minus 1, that is called a lagged variable because it refers to the time period before. Lagged coming from the word falling behind or something like that. And since it's an explanatory variable, we'll call it a lagged explanatory variable. To estimate this model in Gretel with a lagged explanatory variable, we go to ordinary least squares. We do the help wanted index as our dependent variable. And now I want to add also the lagged unemployment. So you go to lags, then you can see here in the UN row, if you want one lag of unemployment, that is, you want unemployment at the previous time period, then you should increase this to 1. So 0 to 1 will give you unemployment at t and unemployment at t minus 1. So let's click OK. The way that Gretel displays this fact is through UN, that represents xt, the explanatory variable at time t. UN parenthesis minus 1, that represents xt minus 1. So this represents the lagged explanatory variable. Click OK, and we get parameter estimates of xt minus 10.1 and parameter estimates for xt minus 1, 11.2. So now the parameter estimate of xt has the sign that we were expecting. It's negative. An increase in unemployment in this period will decrease the number of help wanted ads. But we also have a significant effect of the lagged explanatory variable. We can do the same estimation in eViews by just doing quick estimate equation, and here we don't select lags from a menu, instead we just type it up. So HWI, that's your y variable, C, your intercept, UN, and to get the lagged UN, you just do UN parenthesis -1, that's the lagged value variable. Do the regression and we have the same result. So lagged explanatory variables are not the only type of lagged variables. We can also have lagged dependent variables. So the idea here is that we believe that yt is directly affected by the value of the dependent variable in the previous period, yt minus 1. Using our example as a case, we would then claim that the help wanted index depends on what value it had in the previous period, as well as depending on the unemployment rate in this period. This is a very common and useful idea with economic time series, because many time series tends to change slowly over time. So the value today is pretty close to the value it had in the previous period, plus minus something that can be explained by other explanatory variables. So the linear regression model with the lag dependent variable would then look like this. We have the explanatory variable at time t, and we also have the dependent variable lagged one period. Estimation of models with lag dependent variables is just as simple as with lagged explanatory variables. In Gretel, for example, we go to ordinary least squares. Let's remove the lagged x variable and let's add the lag dependent variable. So we need a dependent variable, lags. Click here for the lag dependent variable, and we want one lag only. So just 1 to 1, OK. And you can see that we have the help wanted index lagged one period. Click OK. The estimated parameter for help wanted is 0.994, indicating that the value of the index this month is pretty close to the value it had in the previous month. It's also affected by the unemployment rate, but now since we don't have lags for the unemployment rate, we get a sign which is not really the sign that we want. EViews, equally simple to do lag dependent variables. You just do HWI intercept, HWI minus 1 to get the lagged, and UN to get the unemployment. And we have the same result. So note that when you lag the dependent variable, it actually becomes an explanatory variable. It's a value which is known at time t. So we call it a lagged dependent variable, and it's an explanatory variable in our linear regression model. So we have looked at the idea of a lagged explanatory variable and the idea of a lagged dependent variable. We can combine these two ideas and have both a lagged dependent and a lagged explanatory variable. But we can generalize it even further, because there is no reason to limit yourself to just looking at the values in the previous period. It may very well be that your dependent variable depends on variables, including itself, going back more than one period. So we can generalize this idea, and when we do, we reach a model called the ADL model, the autoregressive distributed lag model. This model has two parameters, P and Q, and these will be explained right now. So the idea is this: yt, we assume that it depends on lagged values of xt and yt, as well as of current values. So then we can specify a linear regression model like this. Yt depends on xt, that's the current value of the explanatory variable. It depends on xt minus 1, the value in the previous period, but it can also depend on xt minus 2, the value 2 period back. So we do this dot 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 to just say that this can go on for as long as you like, ending up all the way back to q periods back. If q, for example, is 5, then you have 5 data parameters, and you believe that the x value 5 periods back will also have a direct effect on y. We do the same thing for the lag dependent variables, and those parameters we call rho instead. So y today depends on the y value in the previous period. It also depends on the y value 2 periods back, and we can let the y variable go back p periods. We need different symbols for x and for y because there is no reason to assume that the x values go back as far back in time as the y value does. So p need not be equal to q. These symbols p and q, we call them the lag length. So q, that's the one for the x variable, is called the lag length of the explanatory variable. And p is called the lag length of the dependent variable. And those are the two parameters that characterize the ADL model. So ADL p, q is an autoregressive distributed lag model where the lag length of the explanatory variable is q and the lag length of the dependent variable is p. Now, so far I've just looked at one explanatory variable, not to make the notation too messy, but it's certainly possible to have several explanatory variables. And you can have lags on all of these explanatory variables. And you can also even have different lag length for each and every one of the explanatory variables. So this is perfectly okay to have different lag lengths. If you have several explanatory variables, you still only just have one q value. And the q value is typically then the maximum lag length of the explanatory variables. That is, if you have two explanatory variables and the lag length of the first one is 2, say, and the lag length of the second one is 3, then q will be 3. So let's talk about the most common ADL models. So ADL 0, 0, that's when you have 0 lag length on both, and that of course will give you the static model. Now you have no lagged variables at all. The ADL 1, 0, that's when you have a lag dependent variable but no lags on the explanatory variable, and vice versa for the ADL 0, 1. You have no lag dependent variables, but you have one lag on the explanatory variable. Probably the most common ADL model is the ADL 1, 1, where you have one lag on each of the x and the y variables. So estimating general ADL model is very simple with econometric software. All you do is just go to the model, ordinary squares, you pick your lag length. For example, I may want to pick, I don't know, just figuring something out here. Let's say a lag length of 3 for the explanatory variable and a lag length of 2 for the dependent variable. So this will be an ADL 2, 3 model. ADL 2, 3. List of all the variables that I will get. Click OK. And all the parameters of the model are estimated. In terms of the notation used in the lecture, this one here, that's an estimate of beta 1. This is an estimate of theta 1, theta 2. Sorry, that's not right. This is an estimate of beta 1. This one is an estimate of beta 2 because that's just the x variable without the lag. This is an estimate of theta 1, theta, hard to click right, theta 2, theta 3, rho 1, row 1 and row 2 right there. So another topic which is not going to be covered in this lecture is the choice of the lag length. How are you going to know which lag length to pick? Well, there's a lot of things to say about that, but most importantly probably is the fact that there is no sure way of figuring out the correct lag lengths. Most researchers tend to try various combinations of P and Q. Another possibility is to look at the T values. For example, the UN3 is not significant, so you may want to stop at the lag length 2 of the explanatory variable, while this one, the second lag of the dependent variable, is still very significant, so you may want to try a third lag of the dependent variable.